additional laws implied by the additive and by all field axioms. So these are interesting because these are additional laws that we get by applying the addition and the multiplication together. So we have A is 0x equals 0. Now, that's very interesting. That again seems obvious, but it only seems obvious to us because we know that it's true. It's not something that's in the field axioms at all. The field axioms are that there's a 0 such that 0 plus x equals x, and that each element has an inverse such that 0 plus minus x, or x plus minus x equals 0. That didn't say anything about multiplying by 0. And with the multiplicative, we have that there's an identity element, there's an inverse, or there's an identity element, 1 times x equals x, and each element has an inverse, x times its inverse equals 1. And we know that the identity element is not the 0 element, but we never said anything about multiplying by 0. But it turns out something about these 5 axioms and the addition axioms together tells you that it must be the case that the additive identity times any number has to be the additive identity. Such an interesting thing because it's something that we all know, 0 times x equals 0, but it's not something that you can deduce obviously. It does not jump out at you from these axioms, but we can show it pretty readily nonetheless. B, if x does not equal 0 and y does not equal 0, then xy. This is an important one. If neither x and y are 0, it's sort of the opposite of this. If these are both not 0, then this cannot be 0. Let me write that again. X, y does not equal 0. See? The inverse of x times y, the additive inverse of x times y equals the inverse of xy equals x times the inverse of y. So again, every one of these in one way or another is relating the addition laws to the multiplication laws. This is multiplying by the additive inverse. This is saying that if neither one of them equal the additive inverse, then if you multiply them together, you're not going to get the additive inverse. And here again, we have the additive inverse times another number. I have a big long equal here, equals the additive inverse of the two numbers multiplied together equals the first one times the additive inverse of the second one. So again, we're multiplying, but we're talking about the additive inverse all the way through. And finally, the additive inverse of x times the additive inverse of y equals xy. A negative times a negative equals a positive. So again, with the field axioms, even what is a positive number versus what is a negative number is actually inevitable. It's implied by those axioms, even though the axioms don't say anything about it. Okay, A. So we want to show that 0x equals 0. So if we take 0x plus 0x, use the distributive law, that equals 0 plus 0 times x equals 0x, okay? Now, using our additive law that if x plus y equals x, then y has to equal 0. We have that x plus y equals x, right? If we assume this is x, then x plus y equals x, therefore, this has to be 0. So we have, right, using this rule, using that if x plus y equals x, then y equals 0, we have that x plus y equals x, right? Here's x, 0x is 0x. Then that means that y has to be 0, so 0x equals 0. That's that one. So for B, we have that if x and y are not 0, then x times y is not 0. Let's assume the opposite and see what happens. So let x not equal 0, y not equal 0. Assume that x times y does equal 0. Then we have that 1 equals y to the minus 1, x to the minus 1, x, y. So what this, okay, I guess I just have to tell you, my cat is laying right up here. So if you see his tail, it's because he's close. So what this means is that if you can take minus 1, or x to the minus 1 times x is 1, right? And then y to the minus 1 times y is also 1. So these all together is 1 times 1 equals 1. So given that, we have that we started by assuming that xy equals 0, therefore y to the minus 1, x to the minus 1 times 0. And we just showed that if we have 0 times x, that equals 0. Here we have 0 times something, so this must be 0. But that means that 1 equals 0. That's a contradiction. So our assumption that xy equals 0 must be wrong, so xy cannot equal 0. Okay. And take this off again. So C, to prove C, we have to show two halves. First we have to show this equality, then we have to show that equality. So we want to show that minus x times y equals minus xy. So if we look at minus x times y plus xy, use the distributive property, we get minus x plus x times y. This cancels out, so that's 0y equals 0. So that shows us that minus xy plus xy equals 0. We know from the same rule that if you have x plus y equals 0, then y has to be the inverse of x. Okay, so here we have two things that equal 0. So if this plus this is 0, then one has to be the inverse of the other. So if we can, so that means that this one has to be the inverse of this one. Therefore, minus x times y equals minus xy, right? Because we have xy plus its inverse equals 0. So that means that this one has to be the inverse of this one. So that's the first half of the equality. So now we're going to prove the same thing, which is it basically goes the same way. So we're just going to do, to show the second half. So the second half is to show that minus xy equals x times y. So it's virtually the same thing. We have that x again, we can use distribution to take out the x. So we have x minus y plus y. That means x times 0 which has to equal 0. So that means that this plus this equals 0. So once again, if we have that xy plus something equals 0, then this number has to be the inverse of that, which means that x times minus y equals the inverse of xy. Therefore, we have what we wanted to show. We have minus x times y equals minus xy, that's what we showed here, equals x times minus y. Okay, that's again just an obvious rule that you can move the minus sign wherever you want it. So what's the last one? The last one is that if you have two inverses multiplied together, you get the same thing without the inverses. So xy equals minus times minus. A negative times a negative equals a positive.
A negative times a negative equals a positive.
So D. So to show that minus x times minus y equals xy, we have that minus x times minus y. So now what we're going to do is we're going to use what we just showed here. So we have that minus x minus y equals minus x times y, right? If you have a minus, then you can take that minus out. That's what this rule proved. So minus x times minus y equals the minus of the whole thing, minus x times y. Now, apply the rule again. This rule, we have minus of minus xy. And now what do we have? We have a minus minus xy, which if we look at the rule D for the addition laws, the inverse of the inverse equals the original. So apply that here and we end up with xy. So minus x minus y equals xy. And that's the last one. Here's an interesting question. What's the difference between this rule and this rule? This rule is only about the addition axioms because you're taking the inverse of a number and then you're taking the inverse of that number and you end up with the original number. There's no multiplication involved here, even though it kind of looks like it. This is just taking the inverse of a number. So that's purely addition axioms. This one is not just taking the inverses, then it's multiplying them together. So yet again, it's combining the addition axioms and the multiplication axioms. Okay, so with the next video, we will start with an ordered field, and then we'll look at some properties of ordered fields, and so on. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.